Hey everyone, so in this video, which is really advanced, we want to look at a couple more ways of looking at points, because so far we mainly work by searching in a certain distance. But sometimes you need something more specific. You want to look in a certain direction when working with point clouds. And the setup to test this is a little tricky to set up, but I decided let's do it together because it might be a nice thought process how to approach this. So what we want to do is we want to look around one particular point that we create with an add node. So there's our point somewhere, and we want to see what we find around it with certain functions. So let's start with a near points function with a normal point wrangle, and we want to check all the points in the second input and see what we find. So what we can do is, of course, we need an integer array, so near points from the second input. And let's quickly cheat how the near points function worked again. Oh, yeah, right, we need a point and a max distance. So point is a position, so that's straightforward. So our current position of our point, and then let's add a max distance so we can limit how many points it finds. So here this works, but the problem is we can't see anything to test it. So let's add a debug attribute. So again, it's a bit odd. We need an integer array. Let's call it endpoints again. And we get in there what's in endpoints, the internal variable. But what you can see now here, it shows me all the points it found in the second input. Now this is cool, but the weird thing now is we want maybe to colorize all the points that we found. Oh, that's a tricky problem actually, because we can't colorize points in a second input. I mean, one option would be to create a point for everything that we found. That would be an option. But since we can only change what is in the first input, because that's what comes out in a second, let's actually turn around the whole thing. And this time we want to do the near points of the current geometry. And the position, of course, is now the one in the second input. So let's fix this quickly. So let's move it around. And I'll call this P2. And of course, we have to read this out. So P2, of course, is the position of the only point of the second input, like this. And now what we can do is we could change all the point colors of the points that are found here. But currently the weird thing is we do this for every single point, which is not what we want. So this is a bit confusing because this gives us all the points that we found relative to this point. And we could check if we're inside of this array, but this would be inefficient because we would do it for every single point. A better approach is to just do the whole thing just once. And then we run through these points, and what we get out of this is the point number that we can just then change. So what we do is for each point, let's call this PT in endpoints, we run over this so that we only run through the points once. We only have to calculate this whole code here once, not for every single point. And then for every point that we find, we set a point attribute. So this is how it looks like. Name of the attribute, then the point number, then the value. So the attribute we want to set is CD. The point number is what we just found, so the PT. And then let's give it a red color like this. And something was wrong. Yeah, one bracket was missing. There you go. And now you can see here, there is a red center. Let's make this a bit more visible by just copying a couple of spheres onto it. Ideally, the points should be primitives so that we don't waste too much geometry. And then it looks like this. So the cool thing now is we can adjust now the max distance and we can see what it finds on this relative to this position there. And maybe what we could do is do a second one only for the center, make this one bigger, and then merge that together. And then it's a bit easier to see what we actually did here. So there's our base position. And if we increase the max distance, we can see what it finds around it. Now, I could have just showed it to you directly like this because it's not so much about the code, it's about the logic here. But I, thought maybe it's interesting to you how to do this. Again, there are other ways of doing it, but there are a couple of interesting things in here, maybe. So this is how you could set something up like this. And the problem again is we can only search for things that is close to us. Not in a certain direction or something. Sure, we could read out, okay, the vector towards that point and then filter it for a dot product or something like that. That's possible. But there are actually functions to do this for us. So let's use this, and that's actually what I wanted to show you, because besides near points, there's an interesting function that I use occasionally that is called PC cone. And like the name suggests, this thing looks into a certain cone and looking for points. So the logic is like this. It gives back, as you can see, an integer array. So all we have to change is this here. So let's do this. So the whole thing is called PC cone. And first the geometry, and this is the first input, just like we had with the near points. So the first geometry. Then we need a p channel, which is a string. This is just the name of our point attribute. This is because you can actually search for other things like color and all that, but this is another topic. And we want to check it against a position. Oh, wait, it's not p attribute, but it's actually the 0.2 of the second input, because we want to check relative to that thing. And now it gets interesting, because now we can add a direction, which of course is a vector. And we want to look into, let's say, z, which is this direction. So let's say set 0, 0, 1. And then it needs an angle. So because it's a cone, it has an angle. And this angle, you have to be careful. I don't think it explains that in the help. Now here, it just says angle. This angle is in radians. So if we want to work with degrees, which is more natural, then we have to first convert it into radians, and then we can type in degrees, maybe 20, for example. And the next thing is max distance. We already have a parameter for this. So max distance. Oh, no, it was called max dist actually. And then it definitely needs max points. So this is something that you can't leave away. It needs a maximum number of points that it returns. Keep in mind, let's call this max points, which is supposed to be an integer. This is not the number of points it will search for, but the number of points it will return. It will always search in all the points. This is simply how many we will get back. So let's look through this. There it is. And so far we don't get anything, and that is because we don't have the max points yet. So let's increase that. And here you can see how this whole thing looks like. We have way too much code and way too little result. So here we go. So by increasing the numbers, this is what it gets back. Let's add this to 1,000. And the max dist is the length of the whole thing. And actually, let's also add the degree of the angle on a parameter, because then it's a bit easier to play around with this. There you go. And let's quickly look at this, because it's easier to see through the sphere setup. And here you can see how this works. We have a max distance, and we have an angle that we can look at for certain points. And this, of course, as you can imagine, allows you to be more specific about your search algorithms. Now, another one to the PC cone, in case you need something like that, is a PC segment. The good news is once you've understand one, the other one is easy to understand too. So this one looks like this. We have a P channel again, and then a first point, and then a second point, and a max distance. Okay, so let's play around with this. So let's redo this. This is called PC segment. So we read out again from the first input. We want the P channel to check. And now the first position is, of course, the position of our point. And the second position is how far forward we want to look at. So for example, what we could do is we add to the P2 a vector of, let's say, 1 meter in Z. And then you can see how it works actually. And then we add again a max distance. So that's the same as before, max dist. And the last one is max points again. Okay, we have that with the integer max points. Good. So let's close this off. There you go. Let's make sure we can kind of see the code. And here you can see it's a bit like a pill or something. So let's look at this in a nicer way. There you go. So let's change the max distance, because then it's a bit easier to see. We have basically 2 points, this point and the point we look forward in one direction. So if I increase this to 002, we move further forward. And here you can see it now looks in a certain, in a pill shape. And this can be really helpful to, look into really specific areas. So that's PC segment. There's actually a fourth one that is worth knowing, and that is a straight line, not like this, you know, in a certain area, but just a straight line. So basically like a ray that is looking in a certain direction. And I don't want to go too deep into this because it's a bit more complicated because it uses pointers again, but the name of the function is intersect. So this could be something that you could use if you want to look for one particular collision basically in one direction. So if that interests you, look into the intersect function. I think it would be out of the scope of this video, but for you to know it exists. This is not in a certain area looking for points, but looking for basically a position that it finds on another object in a certain direction. Maybe I will do another video about this at some point, but I think the most important ones for now is that we have near points, where we can check points based on a certain distance. Then we have PC cone, where we look into a cone shape, and we have PC segment, where we look into kind of a pill shape. And depending on what you need, this can be really helpful to have for certain problems. And let's really quickly, because I don't want this video to be too long, look at some examples of this. And where I used this, for example, in my case, it was a much more complex setup, but this is basically a traffic system. And what we can do here is we can check if there are pedestrians in the cone shape of a car, and if the car finds it, it will stop. So if you need something more complex than just looking for the closest point in a point cloud, but maybe want to look in a certain direction, then PC cone or even PC segments can be a really good alternative. So I hope this is helpful. Remember that when you need it. So thanks very much and see you later. Cheers.